We are in Rosen, Discrete Mathematics and its Application, section 10.7, where we'll finish our discussion of Euler's formula and discuss Kuratowski's theorem related to planar graphs. We have one more corollary to Euler's formula to discuss. That's corollary 3. It's similar to corollary 1. We have a connected planar simple graph with E edges and V vertices greater than or equal to 3. And in this case, we have no circuits of length 3. Then the number of edges is less than or equal to twice the number of vertices minus 4. This proof is requested in exercise 15. It's very similar to that that we showed for corollary 1, and it uses the degrees of regions to make the proof. All right, so the reason that corollary 3 is valuable is corollary 1 does not detect that K33 is non-planar. It did detect that K5 was not planar, but corollary 1 doesn't do so since the test is 3 times the number of vertices minus 6. That's 12. That is greater than or equal to 3, so we can't tell that K33 is non-planar by corollary 1. However, since K33 is bipartite, it has no circuits of length 3, so corollary 3 applies. So twice the number of vertices minus 4 gives us 8, and 8 is not greater than or equal to 9, so it fails the test for planarity, and K33 is also non-planar. So K5 and K33 proven non-planar by these two corollaries. And it turns out that these two graphs are related to all non-planar graphs through the following theorem. It's called Kuratowski's theorem. We have one more concept we need to capture before we can state Kuratowski's theorem. And that is, we need to understand the concept of elementary subdivision. And all elementary subdivision is if you have an edge between two vertices in a graph, and if you divide it into two edges with a vertex of degree 2 in between them, you've done what's called an elementary subdivision. And if you have a graph with a vertex, if you have an edge with a vertex of degree 2 between two other vertices, you can either create the new graph of the elementary subdivision, or you can get rid of that vertex of degree 2 by undoing the elementary subdivision. And the next definition takes advantage of that operation by saying that two graphs are homeomorphic if one can be derived from the other by a sequence of elementary subdivisions. Here's an example. We have a graph here, and these graphs here are all homeomorphic to the first graph because all we're doing is creating new graphs by elementary subdivisions. And so all of these three graphs are homeomorphic to each other because they can all be derived from one another by adding or deleting a elementary subdivision. Okay, now we can state Kuratowski's theorem that a graph is non-planar if and only if it contains a subgraph homeomorphic to K33 or K5. Every non-planar graph has a subgraph homeomorphic to one or the other of these, or possibly both. The proof is beyond the scope of our course, but it is important to understand that K33 and K5 are crucial to understanding graph planarity and non-planarity. Let's do an application of that. We have here a graph called Petersen's graph. It's a graph with 10 vertices, and every vertex has degree 3. And if I had to guess, looking at this graph, would K33 or K5 be the subgraph that shows that this is non-planar? And I would have guessed K5 because it kind of looks like K5. But K5 has vertices of degree 4. This one has no vertices of degree 4. K33 has vertices of degree 3. So we will see that that is the homeomorphic subgraph. How will we find it? First, we're going to take a vertex and delete it. So we'll remove vertex B and the associated edges. And now we show that we have 1, 2, 3, 4, 5, 6 vertices of degree 3. The remainder of them have vertices of degree 2. We'll combine them in a way that illustrates the fact that the vertices of degree 3 are in bipartite sets. The remainder have the vertices of degree 2 we can get rid of by deleting the elementary subdivisions, and we can see that K33 is the graph that is a subgraph that is homeomorphic to, is the graph that the subgraph of Petersen graph is homeomorphic to. All right, so that is our discussion of graph planarity, Kuratowski's theorem, and several corollaries related to Euler's formula.